Okay, so we're going to continue with what we started last time, which was on conjugated polymers. As we said, conjugation is the alternation of double and single bonds on carbon atoms, and that as the conjugation size increases, the band gap decreases and the density of state increases. So you can see here in this, we can see here that as we go from one atom to two atoms and essentially increase it to n atoms or become a polymer, then the band gap, the difference between the HOMO, the occupied state, and the LUMO, the empty state, decreases. But even at infinite number of atoms, we still have a finite band gap between the HOMO and the LUMO state. And we said that the band gap decreases and the density of state increases, and these quantum size effects derive from charges in the electron-electron interaction. And this is essentially what you need to know is proportional to the wave function delocalization. So to reiterate, polymer consists of linear arrays of repeat units, right? So one unit is repeated like n times, 20, 40, 60, 180 times, and so on. And these repeat units are linked by covalent bonds. Okay. So we described how we can, we talked about the potential well and how we can define and we can calculate the energies. But the one thing to bear in mind that the potential doesn't have a flat band because we have alteration between single and double bonds and the bond length changes. But it's clear that the extent of conjugation, which we have said many times now, affects the optical and electronic properties, so how absorption and transport, which we haven't talked about yet, occurs, is intimately dependent on the structure of the molecule we have. In polymers, defects and structural deformation within the polymer chain can misalign the pz orbitals. So before we started by just considering one unit length and we were talking about how the pz orbitals delocalize, but in a polymer we actually have repeating units. And unfortunately, the nature of these systems is that they have misalignment. So the pz orbitals are often misaligned, and this breaks the electron delocalization. And as a result, it forms isolated regions of conjugation that act as individual chromophores. So here in this drawing on the right-hand side, where you have basically chains of polymer in red and blue, we're trying to actually depict this. So variation in conjugation length between these conformational subunits gives rise to energetic dispersion of the excited state throughout the material. So if you see in the drawing here, where you have a chain of polymer, I mean, this is a typical defect still in the conformation of a conjugated polymer. I believe this is PPV, a very standard or known polymer in this field. And the red is PPV, exactly, it's indicated here. So if you look at one small part of the chain, the part that has been circled in blue, then it's evident that the pi bond extends over the PV repeat units. But these units are frequently actually disrupted by rotations of sufficient angle, which can essentially or eventually break the conjugation. So you can see you have this rotation here, so this is almost a broken conjugation compared to this part. Long range, just to note, long range Coulomb interaction couples the conformational subunits. And later on, when we talk about excitation and what happens when light is shown, then the disruption of the conformational subunits becomes very important. Okay, but there are also other consequences of these defects and conformations and chromophores of polymers. So as I said, the effects of dispersion is essentially results in homogeneous broadening of fluorescence spectra. We will talk about emission and fluorescence spectra later on, but you can just for now accept that the spectra will actually broaden up, but inhomogeneously. And from this, we can see that the electronic and optical properties, including energy and delocalization of the excited state, energetic dispersion, and electronic conductivity, all depends on chain conformation. And this can be tuned as simply as through the choice of solvents or the way we dissolve the polymer to make a solution, and there afterwards to make a solid state or so on. So all of this is like, is the true nature of a molecular semiconductor. But I mean, I said that this is a true signature of molecular semiconductor, but crystallization is also very important. And it's probably no surprise that in solid state, additional effects come into play. So chain organization and crystallization introduce long-range order and affect intermolecular electronic coupling. And this can be altered by simply heating a polymer film above its glass transition temperature to allow the chains to reorganize. But well-ordered conjugated polymer films enable unbroken conjugation of orbitals over many repeat units. So if you could have had, instead of this thread being so kinked up and broken into different segments, if it was just a one straight line, then we would have had unbroken conjugation. However, while the singlet excitons exhibit delocalization by existing as linear combination of several or many orbitals in an excited state, so we talked about this earlier on, the extent of localization is not just simply defined by the conjugation length of the polymer. There's more to it. The strong electron vibrational coupling in conjugated polymers results in structural changes taking place in response to excitation. These deformations, in combination with fluctuations from the environment, can serve to dynamically localize the exciton. This is what we call as self-trapping. What happens now is that the change in exciton size and excited state character take place over tens of femtoseconds, and this requires for nuclear reorganization. And if you do spectroscopy, this will show up in large stroke shifts between the absorption and emission. So again, to emphasize the competition between delocalization due to the overlapping orbitals and confinement due to electron vibration coupling it has been accepted to play an important role in the process of, in the electronic process or even optical process when it comes to solar cells or LEDs. Okay. So here what we see is, for instance, other things that we have to consider when we're talking about conjugated materials is that when we go from solution to solid state, often when we're making a photonic device, they're actually in solid state. It's not a solution anymore. And the difference between solution and solid state is that often we have aggregation kicking in. So here is the absorption, this red orangish color of a polymer known as PIF-BHD in solution. And the purple is the absorption of exactly the same material, the polymer, but instead of leaving it in solution, we solidified it in the sense that the same solution was taken and made into a solid state by spin coating. And now you can see that the absorption of the same exact material is actually rather different. The peak has shifted, and also we have more vibronic structure in the film. But this is because of the aggregation. So in the film we have aggregation, whilst in the solution we don't have aggregation typically. Okay, so some of the other things to point out here is, for instance, this is a typical donor acceptor polymer. So polymers can either be just a donor part or an acceptor polymer, or sometimes they try to, the synthesis, they try to bridge a donor unit with an acceptor unit, but still it's called, for instance, a whole an electron donating polymer, for instance. So on the acceptor unit, you can see here that we have alkyl chains, and usually the larger these are, the more soluble the system would be. So we put the alkyl chains for solubility. Equally, sometimes some other alkyl chains probe the interchain packing. So to begin with, the chemist made some materials, the physicists or material scientists, they studied this, and after some detailed examinations, they went back to the chemist to say, for instance, if the solubility is too high or too little, or the optical properties or electrical properties are certain things, and it needs to be changed to meet these criteria. So the chemist would go back and play around with the structure to come up with a new material which has the right band gap, but it's also important to have the right HOMO and LUMO energies. And at the end to also have properties, so these band gap and so on, they will dictate where the absorption would be. But it's also important to understand how the molecular structure relates to, for instance, how fast charges can be generated. Here's another example of another polymer that is often used in our field, PCP, DTBT. And again, we're showing what are the accept. This is another donor acceptor unit. Here is the acceptor unit, which is a benzothiodiesel unit, And here is the donor unit, which is essentially a thiophene, but dithiophene. And you have this attachment. So here you can see there is still a little bit of difference between absorption in solution and in film between most polymers. So here is the example of two different, slightly two different polymers. So the PCDTBT part is the same, but the red data is a fluorinated version of it. And we can see whether we have fluorination or not, the absorption changes a little bit. So with fluorination, we go a little bit redshifted, but also the vironic peaks are more defined than when there is no fluorination. And it's also interesting to see that between solution and the solid state in fluorination, there's not all that much difference, whereas in the PCPDTBT itself, there's quite a bit of a difference. But the other thing to note is that, as it's noted here, so when you take the EUV, the ground state absorption of PCPDTBT, you can see that especially in the film, the range from pretty much from 500 nanometer to 900 nanometer is covered. So if you want to make a device where we want the light in this range to be covered, then PCPDTBT is a good example. By looking at the absorption of other materials to see where they cover, then we can combine this polymer with those. For instance, if we have another system where it absorbs above 900 or below 500, then we can say we have complementary absorption material, and we'll get the range from 500 to whatever covered. Okay, so now so now a lot of times we've been loosely talking about excited states, excitons. I mean, not too much, but there have been some refer to it. Okay, so here we'll try to explain things in steps. In general, when we're in ground state, when we don't excite the material, what we have is the situation on the right, on the left here. So all of our carriers are in the occupied state, the HOMO level, and at the moment, ignore the arrows that you see here. All the electrons and holes are in the occupied state, and this is the configuration usually in the ground state. So this is the stable configuration. Now, by different means, we can excite the system. And when we excite the system, we can either put an electron into the lowest occupied molecular orbital, or we can take one electron from the HOMO, and so this one would do this one. And in both cases, what we now have is we have a polaron. So when we have an electron put in LUMO, we have a negative polaron. When we have an electron taken off from the HOMO, we have a positive polaron. And if we have two identical polarons doing the same thing as we do here, it's bipolaron. So negative bipolaron or positive bipolaron. Depending on where the electron is placed, so if we're creating a negative polaron, then we can, for instance, get to the first excited state. So excited state is when an electron is taken from the HOMO, its HOMO, and put into its LUMO, the lowest unoccupied molecular orbital. This gives us the difference between the HOMO and LUMO, which we talked about. It's the band gap, also corresponds to the S1 level, the first excited state level. And again, this can be obtained from optical absorption. The red arrows that you see, they indicate the spin of the material. the spin doesn't exactly mean things are spinning around, but for whatever reason, physicists decided to call this property spin. It's the orientation of the electron with, the orientation of the electron. So in the majority of cases in ground state, in normal state, the spins are paired. So if you have two electrons, the electrons have opposite spin. One of them is pointing up, the other one is pointing down. And the overall spin is 0 because one is positive, one is negative, and in terms of directions, and the net is 0. Equally, when you're exciting charges, again, if you're in the ground state, the electron has a positive up pointing spin. When it's excited, it will also have an up pointing spin. Or if it was down pointing, when it's excited in the LUMO, it will have a down pointing spin. So the red arrows are indicating spin. Now, in addition to singlet, we also have triplet states. Triplet is when the spin is no longer paired, and so now the net spin is not 0, but 1. So here the spins are parallel to each other. That means that one electron is pointing up, the other one is also pointing up. It can also be pointing down, and the other one would be pointing down. And in general, there are 3 different configurations for the triplets. So it's up, up, down, down, or the 1 over square root of up, down, minus, plus, up, down, up. Whereas for singlets, it's just up, down. Okay, so now what is an polaron? When a charge is put onto a molecule, so either we put it into a LUMO or we take the one charge, one electron away from the HOMO, its nuclear coordinates will has to adjust to the new equilibrium position. So now the charge, the charge that's either gone to LUMO or taken off from HOMO, and the accompanying lattice deformation, which results from this move, is collectively referred to as a polaron or a pseudoparticle with an effective mass which is greater than that of the charge alone. So one question might be, how can we actually achieve this? You can create a polaron by chemical reduction or oxidation, by using a dopant molecule, or by injection or photogeneration of charges. So, but regardless of how a polaron is generated, the definition of a polaron is the charge that you have and the accompanying lattice deformation. And sometimes you can call it a pseudoparticle, but often it's more called a polaron. And depending what sort of experiments or in particular optical spectroscopy we do, we can definitely detect polarons in experiments. And in fact, that's how we can actually tell whether we have created a polaron or not. Okay, so to recap, let's have a look at the differences between organic and inorganic terminologies and nomenclature that is used. In classical semiconductors or inorganics, we often refer to band gap, which defines the gap between conduction and valence band. In organics, we also refer to the band gap or energy gap, which is defined by the difference between the highest occupied molecular orbital HOMO and the lowest unoccupied molecular orbital LUMO. In organics, often we just directly talk about electrons and holes. And in organics, we have negative polarons and positive polarons. In organics, when we have excitons, so exciton is a strongly bounded, excited state. And the bounding is with Coulomb bound between the electron and hole pair, and it has a high binding energy. In organic materials, at room temperature, the binding energy is much, much larger than kBT. So the thermal energy, the kBT at room temperature, is 25 milli-electron volts. The Coulomb bound between the electron hole pair, which results in a binding energy, is at least an order, definitely 20 folds or 30 folds larger. And this type of exciton is called the Frenkel exciton. It's localized, strongly bound. Inorganic excitons, however, they are known as Wannier excitons, and they're very weakly bound, which means that actually in room temperature, the thermal energy is sufficient to overcome the Coulomb attraction between the electron and hole and generate free electron and hole. So this is the big difference between organics and inorganics. Organics at room temperature is a Coulombly bound electron hole pair. Inorganics at room temperature, it's free electron and holes. So next, we're going to talk about charge transport in these materials. We'll talk about what is the nature of charge on polymer, how they move, and the most useful is once we know that kind of information, what can we actually do with them? All right. So we just said that in order to have charges, we need to get a polaron. That's the starting point in organic systems, in organic material. And from there, we might be able to get free carriers. So excess of electron or excess of hole in the LUMO or HOMO of a system means we have a polaron. So when we have a negative polaron, we have an excess of carriers or electron in the LUMO. And when we have positive polaron, it's an excess of, lack of electron in the HOMO. How do we measure these HOMO and LUMO levels? We refer to ionization or electron affinity energies. So we always have to measure how much energy we have to put in to generate positive charge on a molecule by removing an electron from its HOMO compared to the vacuum level. This will give us the energy for the HOMO. So we want to, the idea for a positive polaron, we need to have a positive charge on the molecule. So we have to remove an electron from its HOMO. The reverse is true for electron affinity. It's to get a negative polaron on the molecule, then we want to see how much energy we need to put in to take away, to put an electron onto the LUMO from the vacuum level, or with respect to the vacuum and energy level. So the electron affinity is essentially the difference from E vacuum, the energy of the vacuum, to energy of LUMO. So HOMO and LUMO are opposite of each other. Often, whilst in electron affinity or LUMO, we are always referring to an electron being placed on the energy level on the LUMO. In the HOMO, we're taking an electron away. And sometimes we actually say we have a hole in there. So hole is the lack of having an electron. So if you're taking an electron away from the HOMO, it means you have a hole in there. And with polaron, yes, we just said that when we have a polaron, it's not just the charge that has, so if you have a positive or negative polaron, it's not that we have an excess charge on the LUMO or lack of an electron on the HOMO, but we actually also have a deformation of the structure as well. All right, okay, so now we go more towards conduction, mobility, and transport. Okay, so conductivity. First of all, we should say that, or we should emphasize again, that organic semiconductors lack translational symmetry, but instead they have ensemble of localized sites with slightly varying energetics levels, and there is distance between them. So we no longer have band-like transport as would be the case for, say, silicon, but instead we have hopping mechanism. So hopping of electrons between the localized LUMO, or the hopping of holes between the localized HOMO states has to be considered when we talk about movement of organic semiconductors. Okay. So when we have a neat material, we have a pristine conjugated polymer. It has a fully occupied HOMO level, and the LUMO is totally unoccupied. This is when there is no doping, when there is no light, or there is nothing to generate extra charges in the device. So all the charges are all the charges are in the HOMO, and there's nothing in the LUMO. To make a system conductive, electrically conductive, we can either dope the system, P-type or N-type. We can create excitations into the LUMO by light, for instance, so we do light excitation, or we can inject charges from the electrodes. But the importance of conduction, let me just say that, yes, and the pioneering work of these Nobel Prize winners was actually when they saw that organic semiconductors, polymers or plastics, when they are doped, they have electrical conductivity. So here's the thing, often conductors, semiconductors or insulators, as I started in the first few slides, are recognized based on their energy band gap, but the conductivity of each case is actually also relevant. For example, insulators have very, very low conductivity. However, even in insulators, high carrier mobility might be possible because there is charge delocalization. And that's because of the low density of carriers above the what we call Fermi level in the conduction band. So this kind of makes it difficult to have a defined border between insulators and semiconductors, as in some cases, insulators can be treated as wide band gap semiconductors if carriers can be excited to their conductive and to their LUMO or conduction band, either through photoexcitation. So sometimes, or yeah, I was going to say they sometimes call it photodoping, but let's just call it photoexcitation. Or if we introduce an ionized point to the lattice, so we do electrical doping. And this is often the case for instance, the diamond, which has extremely large carrier mobility. Conductivity itself is defined as the product of the free charge carrier density. So the density of the charges within the conduction band and their mobility. So mobility is, as I've highlighted in this red rectangle, has the symbol mu, and it's essentially the velocity when electric field plays a role. So velocity over electric field gives you mobility. It's basically how fast a carrier can move. That's what mobility is. So I was saying conductivity is defined as the product of free charge carrier density and their mobility. So N times mu, as you have here, conductivity equals sigma, that's the symbol for conductivity, equals E, which is the charge of an electron, N is the carrier density times mu. If you want to, I mean, one has to remember that a lot of these things are actually both temperature, light intensity, and field dependent. So even though the equation sigma equals E and mu is written here so neatly, but one has to write in brackets that sigma itself is dependent on N naught, which is the carrier density in equilibrium, the electric field, light intensity, temperature, and the band gap. So it has many dependencies. But you don't, at this stage, don't worry about that. So for now, just learn that sigma equals E and mu. Now, mechanism of charge transport. As I already said, we have this, instead of having a very neat band-like structure in conjugated materials, we have energy levels that are different to one another in terms of both energy and space. And we said that the transport is described by hopping between HOMOs and LUMOs. Besler was the first scientist to suggest that a model for charge transfer based on hopping of charge carriers needs to consider a Gaussian density of state. From this work, it was developed that we need to consider the hopping rate to be assumed to be depend both on the energetic offsets, so the offsets between each LUMO or each HOMO that the charge has to hop between, and the spatial distance between the sites. So this is the case 2 that I am describing. Case 1, charges are delocalized waves. This is band type structure, which doesn't happen for organic materials or semiconductors or conjugated polymers. This is what's the case in very crystalline materials like crystalline silicon. But case 2 is where we have a Gaussian density of state as it was proposed by Besler. And now we consider the rate of hopping between each HOMO, or LUMO, and so on levels. I'll come back to this. Okay, yeah, I'll do this way. So here's an overview of mobility values for different materials. Let's start off with crystalline silicon. You can see crystalline silicon has typically a mobility of 10 to the power of 3 centimeters squared per volts per second. As we go from crystalline silicon to polysilicon, then the mobility drops by 1 or 2 orders of magnitude at the very least. Then we go to amorphous silicon, it drops even further by an order of magnitude. Now, if we go to polymers, especially organic polymers, some of the good ones actually have mobility of the order of 10 to the minus 3. So you can see polymers and crystalline silicon have a difference in mobility of about 10 to the power of 6, which is quite significant. Because of this, it ends up making the performance of the electronic device somewhat different. But we won't talk about that now. Okay, so let's carry on with how transport occurs in disordered medium. So we have 2 types of models that describes the medium, that describes, mathematically tries to describe the medium of disordered materials. So each conformation is a site with different energy level, and we have to see how these sites are distributed in space and in energy. Two models that are used, the first one, which is rather nice and more friendly, is called Miller-Abraham type hopping. We get the rate for jump from site J, or from site I to J, with the energies of E, I, and E, J, which are at the distance delta R apart. So here is the equation. This is the W is the hopping rate. Nu naught is the attempt to hop frequency, or the attempt rate, phonon frequency. And R is the distance between each site that it has to hop. So imagine this is all the HOMO, or all of it would be the LUMO, and R is the distance between each hop that it has to take. And now we have the exponential part, which considers the energy difference between any two sites, site I and J, or site 1 and 2, with respect to the Fermat energy kBt. So already what we can see here is that when a charge hops down, there is no penalty for that. That would be rather easily achieved. Yet when it wants to hop back up, so for instance, from this Ri to Rj, it needs to overcome this barrier in energy. And we have to see what sort of energy this is compared to kBt. Sometimes this barrier is rather large and the charge gets stuck or gets trapped on this side. And given that the energy required to detrap this is larger than kBt, it means we can't do it by itself. Sometimes we can apply an electric field in order to get those charges out, or in order to give a particular direction to the charges to go from one side to another side. So we can just modify the Miller-Abraham equation to include an electric field in the exponential part. So one important thing here is that in this formalism, there is actually reorganization of molecular structure which has to be taken into account. So every time the charge moves around, the molecular structure has to spend some energy to reorganize itself. You remember when we said the polaron, the definition of a polaron, it was the charge plus its deformation of the lattice. So that's the reorganization needed to reorganize the molecular structure. Sorry, that's the energy needed to reorganize the molecular structure every time the charge carrier makes a movement. And this polaronic nature is not actually included, and the electron-phonon coupling is thus limited to the thermal activation of the charge transfer step during the process. So this is one of the limitations that the Miller-Abraham disorder has. So as I said, in this description, the model takes into account that there is a penalty on hopping rate for hopping to distant sites that the size is higher in energy, but there is no explicit consideration of the reorganization energy. We should also point out that while jumps to and from distant sites without energy difference have identical transition rates, so if there happen to be two energy sites on the same energy levels, when you jump from one to another, it's the same rate. This is not the case for sites with an energetic offset, of course. Also, an important consequence of this is that the sites that are very low in energy can act as traps, which is what we just talked about. That's why sometimes you might, if the charge is trapped, you might need to have a field to help that charge get out or not allow it to get trapped to begin with. Okay, so to remember is that when we have during macroscopic charge transport, we have a large number of sites with different energetic and spatial distances. And this is felt or sampled by each charge carrier. This corresponds to a multiple trapping and detrapping mechanism of charge carriers, where the trapping time of every site is determined by the corresponding hopping distance and the energetic offset between each site. So Besler's model takes this into account by assuming the Gaussian distribution for the site energy EI, we call it EI, and the jump distance, which is delta R, with the width of a particular disorder, sigma. And let me jump a couple of slides ahead, actually. So this is what I'm describing here. So neighboring molecules with dipole moment in different directions or energetic disorder. And I'll come and explain this again, but I'm just giving you an introduction. So the sigma that I was saying is the disorder, the width of the jumps that they have to do. And by using Monte Carlo simulations, one can yield a formula describing the electric field and the temperature dependence of the mobility of charge carrier hopping in a disordered material. So it's this equation here that actually looks a bit ugly, but it's not particularly that bad. So as you can see, it has the zero field mobility, which exponentially depends on the energetic disorder over kBT all squared, of course. So you might be asking, why do we have energetic disorder? Why do we need to use a Gaussian density or distribution? Then the reasons for energetic disorder are numerous. For instance, it could be because the neighboring molecules, they have different dipole moment in different directions. So this kind of distorts the electrostatic potential, the microelectrostatic potential, and creates disorder. So this is what we call polarization. Over here, molecules in glassy state, they have different conformation, different site energies, then this gives you intrinsic disorder. So there are reasons why we can have energetic disorder, and for sure we have a lot of energetic disorder in polymers. This is why we actually need to use the Gaussian disorder model that was, I just talked about it from Besler's model. With the Gaussian distribution, then it really takes into account that the width of the Gaussian distribution corresponds to the energetic disorder. So the larger the energetic disorder, the larger the width of the Gauss. And that most of the charges are situated approximately by the amount of energetic disorder squared over kT. This would be below the center of the density of state. So here in this drawing on the top of this slide, you can see the center of the density of state is approximately halfway between all the, if you consider all the energetic sites that distributed, halfway through it would be the center of it. And that should correspond, if you draw a Gaussian distribution, it should go through the center of it, so through the peak. And most of the charges by statistics, it's just pure statistics, Boltzmann statistic, should sit below that. Sorry, below, yeah, exactly, sigma squared over kT below the center. And for that reason, because they're below the center of the density of state, most charges move along states that by the same amount, sigma squared over kT, below the center of the density of state. So eventually we get this equation where the effective activation energy, that's the activation energy required to get a charge from a lower site to a higher site, is half of sigma squared over kT. So now we can write an equation for mobility, which is either in terms of activation energy or in terms of disorder. They're exactly the same thing, depending on which one of these values, parameters we have. We can typically get them with different measurements, so we can use either version of the equation to get the real mobility. Now, how do we measure mobility or disorder, or what are the techniques in general that are often used to experimentally determine the charge carrier mobility? There are several well-established techniques. One of them is this technique known as time of flight. Time of flight is a time-dependent experiment. We call it it's a time-dependent experiment. It was first used in the 60s for silicon. So once we learned that, we tried to adapt that to work for organic or polymer systems as well. So the way it works, the system that you want to test, the polymer, the plastic, the material, has to be sandwiched between two electrodes, and one of them has to be at least one of them has to be semi-transparent. Why does it need to be semi-transparent? It's because we need to shine light on the system, on the polymer, to generate charges. If it's not semi-transparent, then there is no way of there's no way of light being absorbed by the material. So you can either have one of the electrodes semi-transparent or both of them. We use a pulsed laser. It's typically about 10 nanosecond pulse width to photogenerate a package of charge carriers close to one of the electrodes. So depending on which electrode, let's say one of the electrodes is only semi-transparent, through that electrode, we excite the charges, and most of the charges that are photogenerated are very close to that electrode. Then we apply an electric field in the reverse to extract, to drive, extract means drive, through, to drive the charges out through the sample. What this means is that when we apply an electric field, these photogenerated charges, they are pulled in one direction, and it has to be in the direction of the opposite electrode, because we want the charges to go through the entire semiconductor, the polymer, and reach the opposite electrode, and we want to see how long this takes. So to do this properly, we have to apply the extraction of the charges instantaneously as we turn the laser light off, right? I won't go into detail so I don't confuse you, but we have a pulse. We get photogenerated charges, then we turn the laser off, and then we extract the charges. When we're extracting, we're allowing the charges to transverse through the active layer, through your material, until it reaches the electrode. The movement of the charge carrier package, or just the charge carrier, it causes a transient current in the external circuit. and we can record this using an oscilloscope. So now, so far we have a laser, we have a apparatus that allows us to apply a particular voltage, and we have an oscilloscope. Using the oscilloscope, obviously we're seeing how the photocurrent is changing. And one thing we can definitely monitor is the transit time for the package charges to go through the sample. We must know the thickness of the active layer, and then using the equation mu equals d. No, I don't have the equation here, that's not very clever. Mu equals d over transit time times field. So transit times multiplied by field is all in on the denominator, and on the numerator you have the thickness of your field equals the mobility. So if you look at, this is the apparatus set up on the left. You have your device, you shine light, this is your laser pulse, you shine light, you apply an electric field. Well, before you apply an electric field, this is your laser light, and you apply an electric field, and what happens is that these charges start to go through the device. So in reality, we are plotting the photocurrent, just the current, let's say, through the device. Initially, we have a little spike, then it plateaus in an ideal situation. So as time goes by, the current stays constant more or less. And when the charges reach the electrode, then we start to have less current, less charge in the device, which also means we have less current in the device. So the photocurrent goes down. To calculate the transit time is the intersection, here I show it better, kind of. If you look at this graph over here, is the intersection of the tail, so where the current is going down, that's the tail, with the plateau area. The intersection of that gives us the transit time. And we can do this experiment with changing both the voltage that we apply, but also we can do it with changing the time between when the laser is turned off and also when the extraction happens. But let's not consider the latter for now. So here's again a structure of your device. You have your semi-transparent electrode here, you have your polymer or material you're interested here, and you have your other electrode on top. The ITO, we know is semi-transparent, so you shine the laser through this side. Most of the charges are generated near the P-dot PSS ITO surface, or sorry, P-dot and your polymer surface interface. Then we turn the laser off and we extract the charges. This makes the electrons, in this case, to propagate all the way through the active layer, through your polymer, until they reach the interface with aluminium. Before they reach the interface with aluminium, the current should remain constant because none of the charges are leaving the device, so the current is not changing. Then as soon as the charges reach the aluminium interface, then the electrons are being extracted, they're being taken away, so there are less charge, which means there is less photocurrent, and we see that the photocurrent starts to drop and we get the tail. This gives us the mobility in this configuration. It gives us the mobility of the electron. If we want to measure the mobility of holes, we have to be able to photogenerate through aluminium. So we have to make a very thin layer of aluminium such that the light can still go through it and be absorbed by your polymer. Then all of your charges are generated at the interface between aluminium and polymer. And now when we apply a reverse bias, all of the charges, i.e. the holes this time, move across your polymer until they reach the P dot PSS ITO, and then after that they get collected or extracted, which means that's when the photocurrent goes down. We can also do this experiment as a function of temperature, and in fact most of these electronic mobility measurements has to be done as a function of temperature for us to understand better. And if you plot mobility that you calculated, so we said mobility equals thickness of the polymer, of the active layer, all over field times the transit time, you get the mobility. So plot mobility as a function of 1 over t squared, and this will give you a linear line, the intersection of which will give you the disorder. Of the density of state. So in addition to time of flight, there are other methods, as I said. Another well-established method is SCLC, space charge limited current technique, or creating transistors, we do OFET experiments. OFET in particular is not good because you have to make a very thick solar active layer, and when the active layer is thick, that means that the mobility is not exactly same as when it's thin. Mobility is carrier density dependent. As we said, because we have traps, if we have systems where carrier density is very, very high, then some of those carrier densities can fill up the traps, and then essentially other carriers are absolutely free to propagate through the active layer, similar to a band-like structure, because now all of the deeper lying traps are filled, so new carriers cannot occupy those states, and as a result we get much higher mobility. So you can see, for instance, in P3HD, when it's measured with OFET, it's about 2 orders of magnitude higher than when it's measured with time of flight. Yeah, this is also another nice example of this different techniques. So in the lost polymer, you can see that for measuring in time of flight, or SCLC, we get a mobility of the order of -2. When you do OFET, it's at least 1 order of magnitude higher. So there is a very, very clear difference between measurements from OFET and SCLC, or time of flight. So once we know which method we should use, then we can also try to correlate mobility values that we get with morphology, whether it's amorphous, crystalline, polycrystalline, or what. Generally, you can see when the system is amorphous, the mobility is very low, but as it turns out, it goes to more crystalline material, then the mobility increases. Okay, I think that probably should be enough for this session, and next time we'll carry on with carrier mobility and backbone orientation.